Did she? I'm putting it on the Google Drive that nobody looked at because I can see that. Huh? We'll tell her later.
Okay, guys, good morning. I said I would send the answers out to the Diene, but I forgot to. They're actually in the packet. The answers to these Diene questions. Okay, I put them upside down so you wouldn't look at them easily. They're actually already there. How we do on these? Is there any questions about these? Is there a particular one you'd like to work? We did this one in class. First one, yeah? How we do on the rest of them? Any questions about these? Question? Which one? What did you get for the answer? I can't see. Bromine, double bond with bromine. Okay, someone suggested we do this one. Let's see how it goes. HBr. Do we have a diene? Well, what do we have here, okay? It's a benzene ring. We don't do any chemistry in organic one with benzene rings, okay? Even though they have pi bonds, it does not act like an alkene, it does not act like a diene or triene. It has very special reactivity. We do not react them in organic one. Up here, this is the diene. If it had a third double bond, it'd be a benzene ring, and then it would have no reactivity. Diene will react. HBr, it's conjugated diene. Okay, which double bond we're going to react? Well, we have a choice because they're not the same. We need to look at them both. If the top double bond reacts, where are we going to leave cation? Top or bottom? Bottom, correct. So H plus. These electrons swing out, and we get UH there, plus here, double bond there, that's connected, right? I'm just going to draw that as phenyl. We would get this, resonance stabilized. We can do resonance structure. By the way, this is tertiary. Resonance structure, windshield wiper this up. And we can get double bond there, leave plus here, UH there. So that's a resonance structure. It's a delocalized cation, and this has secondary. You cannot do resonance into the ring. That's it. But we have a cation that has tertiary and secondary characteristics. What if we react down here? We're going to leave cation on left or right? We're going to leave cation left or right?
Right.
Right, why? They'd both be secondary, but this would have resonance. It would have resonance from both. So we're going to have H plus here, and we're going to get UH there. Plus here, and that has the benzene ring. I'm going to draw it out here. Can we do resonance of this? Yes. Electrons down, swing down, windshield wiper down. Down plus here, UH there. This is tertiary, and this is secondary. Which is better, tertiary secondary or tertiary secondary? Well, that's the same. But hold on. We can do additional resonance structures here, because this is a benzylic cation. Positive charge is next to the ring. It's A, but we can also windshield wiper this way. Plus there. Basically, this is a benzylic cation. It's also stabilized by the benzene ring. Over here, you do not get that stabilization. I mean, we could draw the ring in, but because the plus never falls there, you can never windshield wiper this over. Two resonance structures, tertiary, secondary. Multiple resonance structures, because we can actually keep going. And if you don't keep going, you see that you have tertiary, secondary, tertiary, secondary. Because this is resonance stabilized here, that's your best cation. So once we do that, we're not doing this over there. This is the way it goes. Now here's the new H. HBr heat, which product we're going to get? The next step, Br minus adds here or here. Because you get your two outcomes by just adding to the two different resonance structures of the diene. So where are we going to add? If we add bromine here, the alkene would be tri-substituted. If we add bromine here, the alkene would be what? Tetra-substituted. So the bromine adds here. And our final product is, I'll just draw that as phenyl. Boom. Bromine here. There's a new H here. Since the H is here and the bromine is 2, 3, 4 here, it is a 1,4 addition. And don't forget the methyl. And here it is. It looks like you got it right. Did you have the methyl on yours?
I forgot it. Yeah,
No, I don't think you had the methyl. So good. Not only is this alkene tetra-substituted, the pi bond is also conjugated with the benzene ring. How do we do on that one? Other questions? Yes?
Why is it tetra-substituted?
Why is this tetra-substituted? Because there's 1 carbon, 2 carbons, 3 carbons, 4 carbons. Yep. Okay, the other ones are, the answer key is there. If there's no other questions, let's look at Diels Alder. Okay, Diels Alder, first off, make sure you can add. 4 plus 2 is 6. Good. Four plus 2 is 6. 1, 2, 3, 4. That's your diene. Has 4 carbons. There could be declarations on it. 5, 6. 1, 2, 3, 4, 5, 6. Those are your numbered carbons. This is a pericyclic reaction. I'm sure you can find that on Wikipedia or in your textbook. Pericyclic reactions are reactions that have a concerted cyclic transition state. Mechanistically, down here, single bond made between 1 and 6. Single bond made between 5 and 4. Double bond ends up between 3 and 2. Basically, the double bond is like two arms. One of these arms has to go bond over here. So we just take one arm. Somebody pull my arm. Go make bond over there. Here we go. Pull one arm, go make bond over there. Well, one of these pi bonds has to break and go make single bond here. This pi bond moves up here. That arrow movement gives that product. That's the same arrow movement that's shown there. What's really going on here? It's really p orbital overlap. It's almost like resonance between two different molecules, and it leads to a new product. Of course, when you do that, it's no longer called resonance. It's a reaction. But if we look at, we got p orbitals, right? One electron makes pi bond. One electron makes pi bond. Here's your diene. We know we have overlap between carbons 2 and 3. We've talked about that. Then you have this guy over here. I'm going to do it with just a single pi bond. One carbon with just one pi bond. There's your alkene. Now, if these were connected, we would say that these could be conjugated. Well, what happens is these two molecules come close enough, and these start overlapping. Same thing here. These start overlapping. Well, this is two different molecules, so they're coming together, and through orbital overlap, they're reacting. Well, that's any reaction. Any reaction we've ever done, it's orbital overlap. I mean, if you take an alkene and react with H+, and we do this, you know, we don't talk about it, but it's really the orbitals start coming together, and they start interacting, and that's about this thick. But here, we can sort of look at it. They come together, and then you, basically, this starts bonding, and this starts breaking, and it goes through this sort of cyclic transition state, if you think about it. And sort of voila, the bonds reorganize, and you end up making actually a single bond between 5 and 4 and 6 and 1. So this is more of a theoretical, but if you just move your electrons, this is a good old Diels Alder. There's no intermediate. This is an activated complex or a transition state. Okay? So if we did a reaction coordinate diagram, we wouldn't come up here and then come down. It would just be one loop, and it would just be a transition state that looks here at all these p orbitals interacting. But this gets cumbersome. I mean, how do you actually move these electrons and get to that? This is almost like a resonance hybrid. It's sort of cumbersome to work with. Here's your mechanism arrow for doing your concerted mechanism to get here. Is this reaction favored by entropy? Two molecules reacting to give one. Is that favored by entropy? No, not favored by entropy. Actually, the reverse is favored by entropy. By the way, the reverse is called what? A retro. Retro Diels Alder. It's a reverse. The reverse is very common also. Usually not talked too much at the introductory level, although it's probably mentioned in your textbook. Any Diels Alder can actually reverse. That would be driven by entropy, 1 going to 2. What about 4? Is it driven by enthalpy? Thermodynamics. Is it driven by thermodynamics? Get out a calculator. Or you can assess it. What's being broken here? What's being formed? Look at the one at the top. What's being broken? 3 pi bonds here. Now you got what? 1 pi bond. But what's new? We made 2 sigma bonds. Right? We made that sigma bond and that sigma bond. So we went from 3 pi bonds to 1 pi 2 sigma, which is more stable. Sigma bonds, right? Stable would be lower in energy. Yeah, this is thermodynamically favored. You can do calculations if you want, but we can also just qualitatively assess it. But it's not favored by entropy. Because 2 reacting to give 1, that's not favored. Typically, to overcome that, a lot of times you do need heat for Diels Alder to overcome the lack of kinetic favorability, or not kinetic, but entropic. So what we did there is no different than how you would assess any reaction that we've done before. Okay, this is the simplest Diels Alder. You got to have at least a diene and at least an alkene, but you can have substituents there. And thus your cyclohexene can have lots of decorations on it, substituents. Let's look at the different components. Your dienes. I mean, this is your simplest diene. You can have a methyl. It makes it non-symmetrical. No big deal. You can have dienes in rings. And actually, the one we did with that HBr reaction, the diene was in a ring. Okay? Still a diene. These can still do Diels Alder. What would the product look like with that ring? Well, first off, in terms of reactivity, these are actually quite reactive in Diels Alder, even more so than this. The reason these are quite reactive is because it's stuck in the S-cis form. These are more reactive than these. What is the S-cis form? Well, consider this. This is drawn in the S-cis form. This is drawn in the S-trans form. This means single bond. About the single bond is trans. Because if you look like right here, this alkene is going this way, this alkene is going this way. So that's called S-trans. Now this can rotate. And if you're rotated, then both double bonds are on the same side. And that's called the S-cis form. It's a description, but it's a rotatable bond. We might get later, analogous to this would be like anti. The double bonds are sort of anti. Here the double bonds are syn, which is just a different terminology. But when the Diels Alder takes place, it has to be in this form. Because if you're going to make a ring, if these are going to react here, they have to react. I mean, if this is pointing over here, how are you going to make this 6-membered ring? In the end, it has to be in the S-cis form when it reacts. Why are these particularly reactive? Because they're stuck in that form. This can't rotate and become S-trans. Thus, it's stuck in the required form. Because it's stuck there, it's always ready to react, and it reacts faster. Does that make sense why the ring ones are more reactive? They're stuck in the appropriate form. It doesn't mean these can't react. These are quite reactive. Diels Alder. Now the dienophile, which is your alkene, these often contain electron withdrawing groups. Electron withdrawing groups polarizes the alkene, and it helps make the reaction a little bit easier. You don't have to heat quite as much. It's common for these to have electron withdrawing groups. For example, look at this alkene. It has a carbonyl attached. It's electron withdrawing. Cyano, which is triple bond, electron withdrawing. Some of them may have 2 electron withdrawing groups. These are esters condensed, but it's carbonyls withdrawing. If you have 2 groups, they can be trans or cis, right? Maybe you have a dienophile that is in a ring. And of course, your dienophile can also be an alkyne. The dienophile is just 1 pi bond. Of course, there's 2 here, but only 1 reacts. It's very common for those to be there. We'll do examples where you have these decorations and look at the outcome. Stereoselectivity. The Diels-Alder is very stereoselective and so-called stereospecific. Ultimately, the stereochemistry that you have in your products is maintained, in your starting materials is maintained in your products. For example, if your dienophile here is cis, you're going to be cis in the product. Stereochemistry is maintained. Dienophile. Zip it together. 4 plus 2 is 6. Here's your cyclohexene. Every Diels-Alder is going to have a cyclohexene. But it's going to have these 2 groups here. These 2 groups. Well, look over here. These 2 carbons are now tetrahedral. Here they were trigonoplanar in the plane, so there's no stereochemistry. Other than relative, they're cis. Well, still relative. But what's the stereochemistry now? The stereochemistry now is they can be cis or trans, but here we're dealing with projections, tetrahedral projections. Well, since they're cis here, they're going to be cis here. Now, I'm not going to get into actually showing this, the modeling of it. Okay? So we're just going to make the statement. But ultimately, the reason that the cis is maintained is because there's no intermediate. This is sitting there, boom. Everything comes together, transition state, and product. There's no chance for it to change from the cis orientation. Stereochemistry is maintained. Now, if you take advanced organic, you would probably pull out some modeling and look at the transition state and all this. We're not going to dive deep into that. We're just going to state stereochemistry is maintained. For example, look down here. Here we have the same reaction, except our dienophile is trans. Well, it can still zip together. This looks like it's in the way. 4 plus 2 is 6. Pi bond here. 6, pi bond here. These 2 groups are going to be trans. Stereochemistry is maintained in the Diels-Alder because it's an inserted reaction with no intermediate, with no chance for any change in the stereochemistry. It's actually very powerful. And that's another reason Diels-Alder is such a great reaction. You get very selective or specific stereochemistry outcomes. Does that make sense? Maintained. What about the diene? Is there any stereochemistry there we can look at? Well, yes. I've got a triple bond here. That's okay. But these are the same. And these 2 reactions, the diene varies. Because here, both alkenes are E, or they're both trans, if you look at it. But this one, one's trans and one's cis, if you look at it. And we know that this is stuck like this. The double bond can't rotate. This could rotate. And if that rotated, we would get that. But this is still E and Z. That's still trans and cis. What's the terminology for this difference? That's S cis, this is S trans. S cis. S trans. Well, this is the correct form it needs to be in. But the double bond geometry doesn't change when you rotate around this bond. You zip this together, 4 plus 2, 6. Only one pi bond reacts here, so you're left with a pi bond over there. Double bond here. So here's your cyclohexane, but you got an extra pi bond because your dienophile had an extra pi bond. 2 methyls. If that's 1, 2, 3, 4, 1 and 4 have methyls. 1 and 4 have methyls. 5 and 6 have these methyl esters. Well, they're there. Look at our product. 1 and 4 are now tetrahedral, so we have forward and back. How are the methyls going to be relative to each other? They're going to be trans. Why are they going to be trans? Because the take-home message is the alkenes were opposite, E and Z. That's analogous to trans, thus they're going to be trans there. Now again, I would show you the molecule, the transition state, and why this works out. So it's really just a take-home message. If the alkenes that are opposite, they're going to be trans. Up here, the alkenes were the same. So the methyls are going to be the same. What about stereochemistry? Am I showing all stereochemistry? Example down here. It's going to be plus an antimer. Because we could have showed that dashed in this bowl. What about here? Do we want to say plus an antimer here? Anybody? No, why not? What? That's correct. It's a mirror plane. Thus, the mirror image is the same thing. It doesn't have an enantiomer. Mirror image is the same thing. I'm not sure, do we mention this here in stereochemistry? How do we know there's going to be an enantiomer here? Well, the mirror image is going to be different. So this does have an enantiomer. How do we know it's going to give the enantiomer as well? Now you can think about how this approaches. Is it going to approach one way versus another? You can think about that. What's a more simpler way to know that it's going to have an enantiomer? What if it didn't? That product's chiral. That means it's optically active. Okay? You cannot just create an optically active compound out of the blue. Is this optically active? No. Is that optically active? No. Thus your product cannot be optically active. Optical activity has to be handed down. Okay? If you do this reaction and only get this enantiomer, you're going to get Nobel Prize. You're not going to get that. You're going to get a racemic mixture. And is the racemic mixture going to be optically active? No. You cannot make an optically active product from non-optically active starting materials. That's not optically active because it's not chiral. This is not optically active because you get a 50-50 mix of each, which is racemic, and that's not chiral. Now, if you separate them, each individual one will be optically active. But you can't say that the reaction gives just one. Okay, stereochemistry is maintained. You can see examples from the dienophile or the diene. Now, of course, back up here, why are we not considering the relative stereochemistry of these two groups here? Well, these carbons are tetrahedral, so they're not forward or back. They're in the plane. There's no relative difference here, possibilities here. It's a planar bond. But up here, they're tetrahedral, and one can be forward, one can be back. Okay, the page we were looking at came from the interweb. This is the one that I put together. Basically, the top three examples are a repeat of what we just looked at. Okay? Repeat of what we just looked at. This one down here is an example for you to do. Show the product there. Product of that reaction. First off, how do you know it's a Diels-Alder reaction? Because that's the title of the handout. How are you going to know it's a Diels-Alder reaction in 6 months when you get numerous reactions, you don't know what handout we're talking about, and it's just... How do you know it's a Diels-Alder reaction?
Yeah, the diene and the dienophile.
You got a diene and an alkene, which an alkene can be a dienophile. I mean, what other reaction can you say? You don't have an alkene in HBr. You don't have an alkene in BH3. I mean, what else do you have? Diels-Alder is just pi bonds reacting. Diene has 2 pi bonds, and the dienophile has 1 pi bond at least. Okay? So you got to think about that. When you're out of context, how do you know it's a Diels-Alder? Okay? Because, guess what? This is not drawn with a neon sign saying Diels-Alder. It's not drawn like this. That's not drawn in the S-cis form. If we did, this double bond is trans, or E. What is this one? Is that what trans? Z. So they have opposite. So if we drew one of them trans, the other one would be cis. Okay? So here it is drawn in the S-cis form, which is now it's ready to. But you got to be careful. Maybe you're expected to chart it like this. Now here, it's got a neon sign going Diels-Alder, Diels-Alder. Right? And you come over here, 4 plus 2, zip it together. Now, we haven't seen how you have to maybe flip one yet, but you don't have to do it here. We'll say why. Zip this together. You got to understand your electron flow and what it means. Single bond here, single bond here. What's now between here? With this pi bond here. So we get, every Diels-Alder has at least that, right? What else is here? 1, 4, 5, and 6. 1 and 4 have phenyl rings on them. Here and here. But these are tetrahedral. Are these phenols going to be cis or trans to each other relatively? Trans. If we draw this one bold, we would draw this one dashed. And then there's a cyano here. Now, here's where we cannot tell the stereochemistry, at least I don't think we can. Is this going to be dashed or bold? None of what we talked about said relative between something here and here. We only looked at here or there. We can know relative between here and something here, but there is nothing there. So stereo here, relative to here, I don't think you can tell. It's probably going to be a mixture. Only thing we can know is the phenyls are going to be trans. Now we could have drawn it the other way. It gets complex here. But in terms of the connectivity, there you go. None of these on this page, I think it's stated in there, none of these get into regiochemistry. These are all stereochemistry because we didn't have to consider, is the cyano going to be up or down? Because if you put the cyano here, it's actually the same exact product. Okay? When we get to the next page, you'll see where there's some differences. How about cyclic? Can you show product here? This is just a diene with a one carbon bridge between them. If that's 1, 2, and 4, there's a CH2 connecting 1 and 4. Okay? We can just consider that. Now here's how you do these. Just zip it together like you would and ignore that. Just act like it wasn't there. Zip it together. What does that give? Six-membered ring, pi bond here, right? Single bond here, single bond here. There's a cyano here. Now we just go back and add this bridge back in. It's a bridge between 1 and 4. There's 1 and there's 4. Just go back and put it in if we connect everything nicely. You see that? When you have these bridges, just ignore them. Just put them back in at the end where they should be connected to what carbons they should be connected. CH2 between 1 and 4, CH2 between 1 and 4.
So we're just kind of folding things like a ring extension also. Because then,
It's not a ring expansion. You actually got.
I know kind of folds, but then the ring technically is like well another ring forms, which is bigger.
1, 2, 3, 4, 5, 6. Pretend there's H's there. Well, we need to put some there. Here's a 6-membered ring. Can we make a bridge between 1 and 4? Yeah. 1 carbon, and then have it bridged. So the 6-membered ring, you see the original 6-membered ring? And then I'm holding it by the 1 carbon bridge between 1 and 4. So you can say you got a ring here to ring here. Yeah, I mean, it's actually another ring here. Because if you look at it, it actually contains 2 degrees of unsaturation, 3, 4, 5. This has 5 degrees of unsaturation. It's like it's 2 rings. We do have a handout. Go ahead and pass this out. I'll turn it into 2 stacks. This handout will change your life. Substitution reactions. We'll probably start on these on Friday. Okay, let's look over here. In this example, the dienophile is the cyclic. That's okay. Ultimately, do we have a diene and an alkene? Can we do 4 plus 2? Zip these together. What do we get? Hopefully we get a cyclohexene here. But the 2 carbons over here, if that's 1, 2, if that's 5 and 6, that's 5 and 6. Well, these are bonded here. Importantly, on this alkene, are they group cis or trans coming off the alkene? Cis. It has to be cis because it's in a 5-member ring. Cis. Well, guess what? There can be cis here. So, actually, your choice. We can draw them both bolded. Now, they happen to be just connected like this. Now, you see, 5 and 6 are now tetrahedral. So they can be forward or back. There they were planar. Well, when they can be forward or back, is one going to be back, one going to be forward?
Yeah.
No, they're going to be cis. Why cis here? Well, there's cis there. Of course, it has to be cis. You cannot draw a trans version of this. This alkene is not stereogenic. So there's an example of the dienophile having a ring. Hopefully, it's just straightforward once you see it. Over here, what is this? This diene has a bridge, but it's not a CH2 bridge, it's just an oxygen bridge. This is actually called furan. It's actually an aromatic. But furan will react as a diene. Okay? It will react as a diene. Analogous to this up here. Show the product there. Just forget about the bridge, draw it in at the end. By the way, up here, I drew the 2 bonds dashed or bold. What if I drawn them dashed? It would have been the same exact compound. It would have been the same exact compound, because that compound is not powerful. Plain symmetry. Your choice, either way. You actually theoretically get both in the reaction, but both are the same thing in that case. Okay, what do we get here? You get a cyclohexene, I hope. We're going to get this here. You know, this is condensed for ester, right? I'll draw it out. Ethyl ester. What do we have between 1 and 4? Oxygen bridge. That is, this bridge here is an oxygen with 2 lone pairs. Now, any stereochemistry? Yeah, that's a chiral carbon. Is one of these going to be dashed or bold? Is it going to be bolded? Now, there's no relative here. There's nothing that's relative to. Is it going to be dashed or bold? Or both? Both. Why both?
Because it's going to yield a racemic mixture.
How do you know it's going to yield a receiving
There's
mixture?
nothing to compare it to on the other end of the compound.
No, you're talking relative. You mean here?
Yeah.
No, you're talking relative
It doesn't have
stereochemistry.
any racemic reactants.
If it was just bold, it would be chiral and be optically active. Are either of these optically active? Non-chiral, not chiral. Not optically active. Then the product can't be optically active. You can't just get one. You get both. It's racemic here. And a racemic mixture is not optically active. Now again, we would have to look at the exact modeling of why you get both. Basically, whenever these come together, they're really not coming together planar on the board. I mean, if this is the diene, the alkene can attack, basically the alkene can attack with the thumb up, or it can attack with the thumb down. It can approach with the thumb up or thumb down. And that's how you get up or down here. But again, the easiest way to know is like, okay, it can't just be one, because one would be chiral and optically active. But it can't be optically active because nothing here is optically active. And if that's optically active, you have a Nobel Prize. The reason it's not optically active is because you actually get both in 50-50%. 50-50. Now, this is actually the first step to make Tamiflu. And actually, on the handout I just gave you, or maybe it's the next one, I show you a synthesis of Tamiflu, and they actually do this reaction first. Except they do it, and they only get one enantiomer. That's because they put something in here that is optically active that makes this be optically active. Okay, how about over here, product here? So you see this bridge? We just forgot about it, put it back in. Product over here. No reaction. Why no reaction? No, why no reaction?
Diene is locked in trans.
Because it's why?
Diene is locked in a transformation.
Yes, the diene is locked. Is that the S-cis form?
Yeah.
I mean, if you forget the rings, it's S-trans. We need this to sort of rotate and just come here. Can it do that? No, it's stuck. This guy is stuck in the bad, or the wrong conformation. Since it's stuck, it can't react. So there's a diene that cannot react because it's actually stuck in the wrong conformation, right? Everybody see that? This doesn't react in Diels Alder. It can't. How can I make a ring to you? I can't make a ring for it over here. Now I can. Simple as that. Okay? On the next page, stereo. Regio. Please be looking at this. Which product? You need to understand how there's two possible products when you come to class on Friday. Then we'll talk about which one. But the starting point is understand how you could get two choices. Basically, when you zip it together, does it zip together like this? Or do you need to flip this over and zip it together like that? So is the group going to be down? If this is 5 5 and 6, is the group going to be on 6 at the end or 5 on the end? Okay? So, be ready for Friday and we'll discuss which one you get and how you determine it. If anybody didn't get a little sucker, I see you saved me all the almond joys. Thanks. See some of you in lab tomorrow, right? We'll do mass spec in lab. The group lab report is due next week in lab. I'll give you your the mass spec of your product